Teams, you have 10 minutes remaining. Teams, do you have any doubts? 5 minutes remaining. 1 minute remaining. Teams, your time is over. IIT Madras, you have 5 minutes to present your solution. Your time. Your time begins now.
Mike, I will take it.
First name was second explain कर रहा हूँ. Yeah, so starting with the like B part first, uh, like adding like a weak base in comparative to ET3N, what we have is uh, weak base क्या? I think H उसका उठा रहा है ना?
माइल्ड बेस एसिडिक एसिड.
हाँ तो फिर कैसे बना?
हाँ, ये कैसे बना? ये यहाँ से बना. माइनस यहाँ पे स्टेबल एसिड. लाइक OH को रिप्लेस करके Cl करता है PCl3.
Yeah, so like adding PCl3 to alcohols replaces OH with Cl, which will and adding like and there will be two pairs formed, and as this positive charge is like more stable than this plus charge, it will like Cl will be formed here, and as there can be as this is a chiral center, so a racemic mixture will be formed, and second, this is done. And in C part, we have a gem diol. As only one product is formed, so we believe that this like B part would be sticking as a cyclic ring. So this will be the Z, and in X and Y, we will have let's make mixture. Okay. Like this. I think this or रस्मिक विषय था ना.
ये पहले ये रेसमिक था.
ये रस्मिक नहीं था.
1 minute remaining.
और X क्या है?
इसका मेरे में जगह पर
X is not an expression.
X plus
Okay.
resource.
I think X showed.
फर्स्ट रूट में बनाना.
First year. First का. CL.
30 seconds.
in first part we are predicting a methyl shift, so like the
Strong base.
like the strong base will pluck out the H plus from like the pH OH carbon, and it will like form
Time's
an
up.
ene.
IISER Bhopal, you have 3 minutes to present your solution. Your time begins now.
Uh, for the first case, we have a weak base, so that would kind of undergo SN1, and then that would lead to the formation of a product that is that would be formed due to the carbocation. Then when we have a strong base, Et3N is a strong base, then therefore it would undergo SN2, and the substitution would occur opposite to that. Then when we have a milder base, that is pyridine. So pyridine basically has a lone pair, which would take away the H plus, and then it would undergo SN1 in that case. So we would have the syn product. Then for the Z product, that would be formed would be an epoxide. So the epoxide would be formed, and then MCPVA is the one which will reduce the epoxide to double bond, like the C double bond O to a carbonyl group. So that is there. मैं D बनाती हूँ.
One minute remaining. We will wait till the time runs out. Time is up. IIT Delhi, you have 2 minutes to present your solution. Your time starts now.
So in A, we are trying an SN1 reaction where the carbocation formed will undergo methyl shift, and hence at 1,2 position the syn and antiproducts will be formed. And also in B, we are considering an SN2 reaction where the initial racemic mixture will result to another racemic mixture due to the SN2 reaction that will take place with the help of a weaker base pair.
1 minute remaining.
मुझे थोड़ी पता है, ये बना दो.
30 seconds. Time's up. I see you have 1 minute to 2 minutes to present your solution. Your time starts now.
Okay, so for question A, our proposed mechanism is something like, first I write the structure is going to be something like this. It's a pH with nitrogen, Cl at above, and there's another replacement of Cl somewhere here. B, the orientation will be just be opposite. The mechanism that I propose is basically simple. There is an attack of OH on the PCl3. First, the strong base is going to abstract the hydrogen from OH. Then O minus is going to attack PCl3. Then there will be a methyl shift from here to here. So O will form a double bond and will go out. Then the pH will go here. And some NGP will be showing that the reaction rate increases a lot. And finally, a Cl can attack here from two sides to give me two different products, which are one of them is syn and one of them is anti. And there is one more replacement. This is for the part one. Part A. For the part.
Yeah, for the part B, we are adding on to solutions that are already there. We're just saying that the OH is not being replaced due to the steric, and this OH will be replaced via the SL2 mechanism, where PCl3 will bond like this over here, and then it will go back. This H plus will, this H plus will be there. The positive charge and the Cl will attack from here.
For the part C, I have proposed this structure where one atom is always from Cl. For the B part, that it is going to replace simply Cl. For the OH one, it's going to lose a carbocation and methyl C, and finally attack for 6 membrane for the structure of Z.
Time is up. Judges, do you have any questions for the team?
Can team D explain what's the A and B?
See, A is a syn product. pH and Cl are in the same, and there is Cl at the end as well because of the strong base. And for the mechanism, you are asking for the mechanism also, or just the product?
The mechanism.
The mechanism, as I explained, was like initially the strong base is going to abstract the hydrogen from the OH, which is near the pH, attached to the carbon with pH group as well. The O minus is going to then attack the lone pair PCl3. Then there will be a methyl shift from the middle carbon to the carbon where pH is formed, and the O will going to form a double bond and leave. The carbocation is stabilized by two factors. One, of course, is the hyperconjugation. Other is the NGP, because pH can combine with that carbocation to form a three-member ring. So NGP.
Understood. Thanks. I'm fine.
I would request one of the members of the question-making team to present the solution.
Check, it's working right. Right, so the solution, I think I will clip this. Check, can you hear me? Okay. Right, so let me start explaining here. So the first reaction given is you have two methyls, you have a phenyl that's out of the board, and you have two OHs. And for the reaction, we have PCl3 strong base in a protic solvent. So what happens is you have a strong base. So first of all, your protons get abstracted away. You end up with negative charges on these alcohol oxygens. These are good nucleophiles, and PCl3 is a good electrophile since it has vacant d orbitals. So what happens is you have a PCl3. You have SN2 happening on the phosphorus, and 2 chlorines leave. So the answer here is a 6-membered ring with a phosphorus that has a chlorine on it. There is a phenyl here and 2 methyls on each of these. And the A and B here that I mentioned is, note that it has a 6-membered ring with no unsaturations. This will exist in a chair configuration, which is the most stable configuration. So you draw the chair configuration. These are oxygens, and you have a phosphorus which will have a chlorine on it. There is a phenyl here, and right, methyls. So here the two structures are basically, you have a chlorine in the axial position or you have a chlorine in the equatorial position. If it's in the equatorial position, it's on the same side of the 6-membered ring as the phenyl, so this is A. If it's in the axial, it's B because it's on the opposite side. Any doubts in the first part? Okay. For the second part, you have a racemic mixture of the initial compound, but you have a much weaker base. So what happens is actually you get the same product, but since you have a weaker base, you still have some, and the reason the base is once again important is you had chlorines leave here. If you did not have the base to act as a quencher, the chlorines would once again conduct an nucleophilic attack here, and you would end up with the chlorination, which most of you did. But since you have a base here, it will actually take the chlorines away from the mixture and it will not let it perform a nucleophilic attack, which is why there is no chlorination in this reaction. So in part B, you have a much weaker base, which is pyridine. So there is some still H plus content left in the solution. This means that the major product will actually stabilize to be the axial one due to something called the anomeric effect, where you have these lone pairs stabilizing the sigma star anti-bonding orbital here. So since this is here, it is stabilized and the axial one becomes a major product. That is the answer for the second part. Third part question. And yes, since you have a racemic mixture, you end up with products for both of the things. That is not anything different. Nothing happens to the enantiomeric purity. Okay, for the next part, you take half of the mixture from, reaction mixture from the previous question, and you add catechol and or resorcinol. So what happens here is, once again, these phosphorus oxygen bonds are really stable, they want to form. So you end up with something like, these are oxygens, you have a phenyl here, O. Let me draw the catechol first. Something like this, or in the other case, the mirror for the other enantiomer, because it's a racemic mixture, this just flips basically. So you have a phenyl here, and these go in this position, right? Now this I will actually now generalize, so it could be resorcinol or catechol. Now the important part is, with resorcinol you have quite a bit of distance. There is actually another carbon in between here, which means that you will get, so if you have phenyls on both of these sides and you have a catechol, they are close enough that they will actually be repelling each other. So both phenyls have high electron density, as you know. So the benzene group has high electron density. They will want to repel each other. So that product is unstable and does not form. However, with a resorcinol, you have enough distance that the phenyls can actually be here. So I will draw the structure. It's a bit big. So the product Z is pardon the atrocities in the bond lengths and stuff. And equatorial axial. So this is the product Z, and product X plus Y is basically you have a O and you have a pH. Same thing over here. This is racemic, as you can see. So both copies of this exist. This is one enantiomer, the other one will also exist. And you have the meso compound forming with resorcinol, which has both pHs on the same side. So there is no meso compound in the catechol mixture, but there is a meso compound in the resorcinol mixture. That is the main takeaway of this question. So this is just schematic. You can see that this does not happen with the catechols where you only have the racemic mixture, but you have a meso product with the resorcinol. And for the last question, the D part where you add MCPBA. So just for the sake of it, I'll draw the structure of MCPBA. It's metachloroperoxybenzoic acid. So it's an oxidizing agent, but before it's an oxidizing agent, it's an acid. It will release protons into the reaction mixture, and these bonds will hydrolyze. So you end up with whatever alcohol you had, diol, resorcinol and or catechol, and on hydrolyzing, there are no more chlorines. So you end up with an OH here, PH. And if there is a lot of water, you can hydrolyze it, you can add water once again and get something like this. So that is the answer for this question. Do you have any doubts? Yeah? Mike.
So with the strong base with abstracting two protons, that much I agree with. But we have given key in the second case pyridine is a milder base. How do we justify key we're still abstracting two protons from both the alcohols?
The thing is, it is just a milder base compared to ET3N. It is still a completely effective base. We just said milder base so that there is some proton concentration that is left that is still unreacted in the reaction mixture. Just so you will get a single major product, which is that, the axial one.
And one more thing for question part C, you mentioned steric hindrance. The pH are at quite a distance from each other. So how do we justify steric hindrance is such a major element in that part?
It's not quite steric hindrance. It's a phenomenon known as chiral self-recognition, which is what the question is based on. So with catechol, even though they are quite a distance apart in the drawing, if you can imagine the structure and you had this but with a catechol in here, these phenyls would not be parallel, they would be slightly at an angle to each other. And you have the orbitals here which are electron rich, so they just don't want to be there, they want to repel. So that leads to instability, if you can understand. I'll try to draw, but it's tough to see on a picture. So if you have a pH here, and you have methyls here, these are close, so this is folded up, this is folded down, this is folded up, and these are actually in 3D, they would be pretty close. So you have a catechol, you have your phosphorus, you have an oxygen right here in the inside, and then you have a carbon and two phosphoruses outwards like this, which are at an angle. If they were straight by, they would probably interact well. They are at an angle, so their electron densities don't want to be close by. They will repel, leading to instability, therefore the meso product does not form. Any more doubts? If you have no doubts, we can proceed with the questions.
Well, chemistry is unpredictable. IISER Bhopal, it's your turn to choose the question.
Double twister.
Double twister. Okay.
It is one kilo. It is kilo Kaiser, and 1 kilo Kaiser is 1000 centimeter inverse. If you want to calculate it, but you don't need it actually.
Ten minutes left.
Like, can you explain why dw bond C is going to like pi WCPH and pi star WCPH in the diagram?
It is going to pi star WCPH.
Yeah, like in this diagram, WCO, like DWCO is going, like forming two orbitals. Like one is like bonding WCPH and anti-bonding WC. So, like, how it is happening?
It is a linear combination. Like it is not a common MO diagram which you have seen for the oxygen and nitrogen. It is a linear combination of the MO. That's why it is represented like that. You have not only that D thing, you also have pi contributions, and its linear combination is making those orbitals. So the major contributions from D and pi, and you are getting the pi. And also you don't have to worry about how they are mixing, you just have to focus the energy level of the MOs. Don't focus on its mixing. Focus on the energy levels of those MOs.
And further, how it is what's the significance of going to like P and P plus PH pi? Like there you have five.
P is only P. P plus PH pi is extended conjugation with the phenyl.
Okay.
5 minutes remaining.
In the question is written that the team looked at the absorption spectra and found that 370 nanometer peak and there's a 350 nanometer peak. So in which compound spectra are they saying these two peaks are?
These two, the one which is the NME2 group. Phenyl.
So both the compounds given above?
Yeah, both of them.
And then they have written in part C there's 580 and 450 nanometer.
So the first one, it is the first one, left one.
Okay, so all the four peaks are for the first compound?
No, that is the absorption. Like they threw the light and it absorbed that wavelength. And the second part is, it is the emission.
Okay, that one's just for the first compound and the
Both are for the
absorption
first
are for the...
compound. Both are for the first compound.
Both are for the first
Yeah.
compound.
We are just giving you the examples that in which compounds it is happening.
Acha, but we are talking only about the first.
Yeah.
Okay.
One minute remaining. Thirty seconds. And time's up. IISER Bhopal, you have 5 minutes to present your solution. Your time begins now.
Okay, so for the first question, we know that the two electrons from the d cube orbital are being excited to the pi star orbital. So one electron will be in the lower state and other electron will be in the excited state. But this compound is non-emissive. I hypothesize this is non-emissive because there's also a triple bond interaction and the energy gap is quite high to form the emission spectrum. For the second question, we've said in the B product they've also added a solvent with the ligands and contaminated it, and it produces a yellow color. For the yellow emission, and the A product causes a red emission. Yellow has much more lesser wavelength than red color. That is why due to contamination, the energy gap must have increased due to ligand formation. That is why there is yellow emission. As for the red color, the energy gap is lesser, causing higher lambda, and that is why there is emission of red color. So we are stating that the ligand and the solvent might have changed the energy gaps between the excitation states. With the same logic, we can say that for the twisted version, there is bright blue light, so the lambda is quite lower. The twisted version might have caused the transitional gap between these two orbitals quite higher due to the conformation.
IISER Bhopal, you have 1 minute remaining. Thirty seconds remaining.
Time's up. IIT Delhi, you have 3 minutes to present your solution. Your time begins now.
So for the first question, we can claim that after we attach the dipyridine ligand, the d orbitals of the tungsten gets excited as due to the crowding by the dipyridine ligand. So so its energy state increases and becomes quite close to the pi star WC pH bond. As a result, we cannot find any emission as the two orbitals come quite close to each other. As far as the second part B is concerned, I claim that the 370 nanometer peak is due to the W to carbon monoxide electron transitions, which remains same in almost all cases and is not affected by any of the solvents. Hence that W to pi star CO transitions remain quite same in all of the cases.
So now for part C, सबसे पहले let's start for the second subpart. So we are asked to find a mechanism to justify the absorption at 317 and emission at 451. We believe the initial absorption is from the ground state to the excited state, where the electron, the nitrogen lone pair gets depaired, which is absorbing in 317. And further, the emission process that occurs is when the charge is distributed across this system because it is in conjugation, and that leads to a somewhat resonance stabilized state, the so-called twisted T1CT state. And because the energy of the resonance stabilized state is lesser than the excited state, this is causing an emission in 415 nanometer range. For part
1
A,
minute is left.
we believe the F3C O2 group, a strongly electron withdrawing group, is going to affect the d orbital in the equivalent compound in the diagram given here. It is going to cause it to be of lesser energy, and the initial transition is the transition from the D to the pi star WCPH in the equivalent compound, which is absorbing at 315. The 580 nanometer emission is due to de-excitation from the equivalent pi star WCPH bond into some other orbital in the molecule. And it is also interesting to note that the transition is not involving oxygen groups, as oxygens interact with the triplet state emissions, and it is given the question, it does not interact in the triplet state emissions. The diagram for the second, first part.
Is up. IISc, you have 2 minutes to present your solution. Your time begins now.
Okay, so about part A, there are a few things to notice. Firstly, you're going from a tetrahedral compound to an octahedral compound. The delta, the splitting will be larger in that case, and you've got another CO and you've got a dipyridine. Both of them are strong field ligands. So what I'm saying is your MO diagram will look something like so your D omega CO and D have swapped. These energies are the same as before, but the energy of this has increased, and the corresponding metal orbital's energy will have decreased. And non-bonding. Okay, there's a P over here, and P plus pH pi over here. These two are forming an orbital over here, and these two, oh damn, yeah, yeah, yes, and there will be one over here. So basically,
30 seconds remaining.
yes, this is what is happening over here. This energy is increased and your orbitals are being filled like this and like this. This energy is less than before, and this will not be in the visible spectrum anymore. That is what I'm claiming. Yes.
Although, for the part 2, I'm saying there is neither no PPS transition nor the DW transition, which is why for 370 is not there. For PPS transition, 315 is happening, but it is contaminated by the DW transition. That's what the part B.
I see your time is up. IIT Madras, you have 2 minutes to present your solution. Your time starts now.
Okay, so in the first part, we have dipeptide ligand, which is a weak field ligand.
Yeah, so in the first part, dipeptide ligand is a weak field ligand, and it is also sterically hindered. So when it will, we believe that there would be less energy. Less energy. Huh?
The transition will be from this to this, which is less than this. So the wavelength will be more than the wavelength of red. So so it will be not in visible range.
And as in the second part, the
1 minute is left.
The pH and Me2 ligand is a strong field ligand as compared to dipeptide ligand, and it is also not as much sterically hindered. So it will just increase the energy gap, which will in turn decrease the wavelength, giving us the yellow color. And in further parts, we believe that the extended conjugation is also coming into play, as it's written like there's one radiationless process happening. So I think because of extended conjugation, the further colors are being formed, like the blue light and the UV light.
Time is up. Judges, do you have any questions for the teams?
I really want by portion you have drawn. Can you explain?
That is for the C subpart second. We try to visualize the energy states of the planar one and pi star, and the twisted states of the molecule. And we try to relate the difference in the energies with the wavelengths being absorbed and emitted. With the clean beam, the initial excitation from the ground state to the excited state is where we are absorbing at UB, the 317 nanometer line. And the de-excitation from the excited state to the resonance stabilized twisted state, that is the emission we are claiming for the bright blue light at 451 nanometers.
Okay. And what is happening in the twisted state? What do you mean by state? You have written resonance. What exactly mean that?
And we mean the twisted state as in the molecule given in the question, and the molecule is experiencing resonation because of the conjugation. So twisted state is just the name for the particular state, and resonance is the effect which is causing the lowering of energy.
Yeah, I have no more.
Since the judges don't have any more questions, I invite a member of the QM team to explain the solution.
So firstly we have been given the molecular orbital diagram, which is, you have 5 MOs here. So the lowest one is pi from W and an extended conjugation from TH. This one is pi only from alkylidene. The third one is non-bonding and is dx square minus y square. And this one is pi star, this anti-bonding. And the last one is this one. So here are the 5 MOs. Firstly, it was asked that why we are not getting any emission, and we have also stated that a dipeptide ligand is there. So the thing is, dipeptide ligand has also MOs, Like if we just draw side by side, let me think that these are the MOs for the dipyridine ligand. These will interact with this one. You don't need to draw the exact mechanism, but you ought to know that these energies will be somewhat between these. Okay? So in case if it is excited, the energy spacing is too low. So now a molecule, instead of emitting, can vibrationally collide with itself and non-relatively come back. So instead of emitting, it can collide with the other, because its spacing has become too low, it can undergo vibrational relaxation, it can collide with the other molecules, and it can easily come back, so we are not seeing any emission. That is called, in jargon, quenching. For the part B, we said that we are getting two peaks, a 370 nanometer peak and a 315. We are saying it is pure, and this one is contaminated. And also, we said that irrespective of any solvent, its wavelength is not changing. So it is, in jargon we say non-solvatochromic, and this one its wavelength is changing, that is solvatochromic, but we don't need it. We just need to know that solvent is not affecting this transition. And we have the MO here. And if you also see the figure, the pi, that is the WC triple bond, it is in the core of the complex. So if it is in the core of the complex, it is least affected by the solvent. So it means this is involved in the 350 nanometer transition, and from where it can excite? From pi, where it will go? According to symmetry, it will go to pi star. So this pi to pi star transition is the pure one. Then comes the contaminated thing, ligand to metal charge transfer. Now you see here, we said that initially dipyridine was there, so there was no emission. But when the pH enemy to the ligand was added, like the enemy to donor was added, then it started emitting. So after the addition of enemy to, what happened? These levels changed. Now instead of it quenching, it was not here to quench. Its energy levels are changed. So now it is showing emission. But why is the wavelength changing? How is the ligand to metal charge transfer happening? So this is it has a lone pair. It can do this, 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 and this. It is N. Let's denote the lone pair as N. And where it will go? Pi is 4, so it can go to the pi star. So along with the pi to pi star, which was pure, we have also a N to pi star transition, and or you can say just the lone pair of NME to pi star transition, which is contaminated and which is making this emission radiative. Now comes the part C. It is mentioned that the 580 nanometer light emission is stable under cooling and ignores the presence of oxygen. In the first question, you were given triplet state. Now you have oxygen. Oxygen, it is non-interacting oxygen. It means oxygen is not affecting it. So this, whatever it will be, it is not triplet. So you are left with only one option, it is singlet. So whatever you saw in the 3DW to pi star WCR, instead of that, it is just a singlet transition. Singlet DW to pi star W triple bond CR. But how do you know it is this one? So you have been given two hints. Stable under cooling. Stable under cooling is the same hint like we gave in the part B, that the solvent is not affecting this. In the same way, if the solvent is not affecting this and this thing is stable, like if you cool down your molecule, your vibrational modes also relax, like it's called vibrational relaxation. But this thing is not happening here. Again, you can say it is in the core of the complex. So it is in the core of the complex, but how would you differentiate from pi and pi to pi star and D to pi star? So we are given another hint, which is parity forbidden. Parity forbidden how? This D and pi star, it is the D and the pi star mix with each other. There is some D to pi star mixing occurring. So that's why it is also a partial D character. Okay? So now from D to D, it is forbidden. That is whatever parity forbidden is, that's why you can say it is D to pi star transition. And in the part B, you have been given the mechanism. You just have to figure it out in which of the three processes is there a radiationless process, and if so, which one. You just have to figure out the one process from here. So yeah, in this mechanism, there is one process which is radiationless. The process where you are seeing the transition from the N2 pi star to TICT. Like initially it was this one. It is aligned with this p orbitals of the phenyl group, and after that you are getting this one. Now this thing is not aligned with the phenyl group. So as all of you know, a sigma bond can rotate. Does it need light? A sigma bond rotation of sigma bond, like you see some Newman projections or Sawhorst configuration, does it need light? It does not need light. The same thing is happening here. It does not need any light to do anything. That's why it is radiationless. And that is the answer. Any doubts? Oh. Any doubts?
The questions are once again on the screen. IIT Delhi, please choose your directed question.
IIT Delhi chooses Redox Odyssey.
Redox Odyssey. You're playing a game named League of Legends, in which the main character, Geogesser Agastya, is trapped by the evil Nern's nightmare in the realm of the oxidation abyss, where every compound is doomed to oxidize. He should quickly escape from this abyss to rescue the world from the pentadentate hands of Nern's nightmare, whose intention is to reduce the whole world of Wonder Chem to linear hydrocarbons. Question 1. Agastya found a map, which is actually a reaction mechanism, through which he could get out of the abyss, but it is partially complete. Help him complete the map. Here, the blue circle represents the radical and the red star represents a chiral center. Reaction mechanism for reference. Question 2. After completing the map, Agastya figured out the main reaction as given there. The protagonist now has 4 options for the carboxylic acids to be used in this reaction. He can proceed to the next level if and only if he can produce the maximum yield for this reaction. The structures of the carboxylic acids are given. But he is unaware that the evil has set a death trap. There is one carboxylic acid that will not undergo any reaction at all. And if he chooses that, he will be stuck in the abyss forever. Figure out that carboxylic acid. Also, choose the carboxylic acid that will be the most beneficial for Agastya to advance to the next level. Question 3. Noticing that Agastya figured out the correct carboxylic acid, the Nern's nightmare got infuriated, manipulated the catalyst and changed the course of the reaction. Reaction as given. Instead of the ideal catalyst, he exchanged it with 4 other catalysts. In order to escape the abyss, Agastya needs a passcode. The passcode is the increasing order in which the catalysts produce an enantiomeric excess. What is the passcode? Structures of the catalysts are given. Participants, do you have any doubts? Any doubts? Since there are no doubts, your 15 minutes of thinking begins now.
Just a trivial thing. If you are presenting on the board, please try to write in a bigger size, because we are also noting here for further marking. And stationary, provide them white chalks. Don't provide them colored chalks. First reagent.
Yeah, RR, MN, bracket TIPS, MCP.
Which one?
RR, MN, then the bracket is TIPS, MCP for part
Oh, that is the manganese catalyst.
of the first part.
Yeah, the first part in which you will make the catalyst thing, that thing. But you don't have to focus on this catalyst. You don't have to write the reaction. If you figure out the mechanism, then it's like it's evident whatever you do in part B. If you figure out the catalyst cycle part A.
Ten minutes remaining.
Can you please repeat the clarif you said for the first part?
For the first part, if you draw the cycle, if you draw it, you will get to know some things, and from that thing you can easily solve part B and part C.
What exactly is the cycle?
That part in which you will solve. You the blank space, you have to fill those blank spaces.
Okay. Like, can you tell this N4L is a weak field ligand or strong field ligand?
You don't need it. It is just causing, it is, you can say it is highly steric.
This is another call for any doubts you may have. Five minutes remaining. 1 minute remaining. Thirty seconds remaining. The 15-minute thinking period has ended. IIT Delhi, you now have 5 minutes to present your solution. Your time begins now.
So for the first question, थोड़ा वाला दियो, जिसमें आंसर है सारे. So in the first question, we can just assume that the reactions given as a that the reactions which are actually occurring give us hints to the actual reagents, give us hints to the actual reactants in the reaction.
So for the B part, the second one will be the worst. As can be seen in the C part, they have mentioned that the only change in the reagents given is just a COH with a propane, a cyclopropane attached to it, and it's mentioned that it's changed the course of the reaction, so that must have been the worst one. So this is the worst one. And as for the most beneficial one, the most acidic out of the three will be the one that's helping the reaction the most. So that's why we picked this one as the most beneficial. That is the most acidic because of the CF3 minus I effect. Yeah, and this is the diagram of part A. These are our blanks. So the first one is a radical which gets oxidized to an alcohol and then gets oxidized again to our carbonyl, as can be seen in the B part reaction as well.
In the C part, we can say that the steric hindrance and the inductive effect of the groups attached to the pyridines in the
we claim that the order for the C part is like the first one is 4, then 3, then 1, then 2. This is because like in the case of the first compound, clearly the steric hindrance is way more than the other compounds because the silicon groups attached are significantly bigger, which would prefer a particular enantiomer, the more attackable or like the less hindered steric enantiomeric configuration. After that, like the third also, first of the phenyl rings are out of plane according to us in this diagram. So that is adding an element of steric hindrance. Besides, the NN bonds are very unstable and also connected with the ring. So we predict that this will also be very sterically hindered. Between 1 and 2, thing is the CF3, which is pulling on it will basically free up the lone pair of N. No, it will involve the lone pair of the N more within that phenyl ring because it is drawing out the electron density from within it. As a result of which, Mn will be
30
freer and
seconds
then
remaining.
more ready to attack. And this will make it less prone to like the differences in enantiomer. So this will become 1 and this will become 2.
So adding one explanation for why this acid is the worst. Basically, concept similar to the banana bonding, which stabilizes the first carbocation. So we believe because of the excess electron density at this position, the carbonyl form in this compound will be particularly unstable in comparison
I
to
tell
native
you your
compound.
time is up. IISc, you have 3 minutes to present your solution. Your time begins now.
So I start with, so I start with part B. Okay. And for the part B, the carboxylic acid with the CF3 group will be possessed by the red top, and the maximum yield will be the one with the three inverse cycle ring. Why? Because the, as you, from the diagram in A, there is, okay. So from the diagram, H2O2 is reacting with to form some peroxide, which is verified by the fact that a 6-membered ring with an H and H axial one is converting to a radical. So there must be some presence of peroxide, which must be at the oxygen which had the hydrogen in the carboxylic acid. So we look at the stability of the radical. The radical stability is worse when there are more electron withdrawing groups than there are more electron donating groups, and especially the resonance, which is definitely the worst load is the CF3 due to the electron withdrawing effect, and the best group is CF3. This is also verified by a reaction of in C where they have used a 3-membered ring. For part A, as we have seen, there will be some peroxide formation here. Some peroxide formation must be there of carboxylic acid, which must have an excess OH and hydrogen somewhere, something like this.
One second. This is like going to be a ligand, or it will be involved in a complex involving a complex that has been given as the MnOTF NFL complex. Essentially, we're saying that the reagent is what is found when the MnOTF2 NFL complex reacts in the scheme provided in the center. Yes, and we're saying that the peroxide will not react and it will be part of the complex, it will still be there. And that is because of this, in this part, we're observing that the free radical is being formed, so the peroxide must be till here and till here. We're not able to get the exact form, and after this, it must go back to a form where the peroxide has gone to normal OH.
And for the part C, this explanation is a bit more intuitive without using reaction mechanisms, but what our idea is that we want a catalyst which is supporting one enantiomer as compared to the other. So what I was thinking was that a catalyst which has more asymmetry in itself would act more in favor of certain enantiomers as compared to others. So intuitively, I have come up with this order where the third one is the least asymmetrical, and then 4, 1, and 2. The second one is the most one I'm claiming because basic.
IISc, your time is up. IIT Madras, you have 2 minutes to present. Your time starts now.
Yeah, so in the first question, Mn, paper then. Yeah, in the first question, Mn plus 2, the OH will, like OTF will be, is a leaving group, so OH will come in place of OTF. So we get the first compound as this, and once it is, as it has H2O2 inside it. So H2O2 will get reduced and this will get oxidized to Mn plus 4. And further, in the second reaction, as we need a H dot, so it will get again reduced, and the H dot will be taken by the OH dot, which will be released by this compound,
1 minute
which will result in Mn plus 2 OH N4L plus 1, where like Mn is in plus 2 state, and here Mn plus 2 will again be oxidized to Mn plus 4 as we need a OH dot. And yeah, so treating with H2O2 will further reduce it to this state. And in the second question, this will be the best case because
30 seconds remaining.
Yeah, this is the best case because this being us having a good minus I effect will stabilize the positive charge here, and here because of steric hindrance, this will be the worst case as it won't allow the chiral tetrahedral ligand to form the compound. And C part, this will be the order.
IT Madras, your time is up. IISER Bhopal, you have 2 minutes to present your solution. Your time starts now.
For the second question, we can see there is peroxide and carboxylic acid in the reagents. That is why they would undergo chemical reaction and form the poor carboxylic acid. For the poor carboxylic acid to form, we have to figure out which of the following carboxylic acids would give a more stable interaction. We have hypothesized the best product will be given by the third carboxylic acid because of the inductive web stabilization, and the worst product would be given by the carboxylic acid, which is CF3, as CF3 is a stronger withdrawing group. It will stabilize the carbocation formed. For the C question, we have to find the increasing order for the enantiomeric axis. The order we formulated is the highest enantiomeric axis will be formed by the second one, then the third one, then the fourth one, and the first one. The first forms the least because of the trialkyl silicon bonds that are there that would create problem with the mirror image and superimposing of it.
IISER Bhopal, your time is up. Do the judges have any questions? If the judges do not have any questions, I invite a member of the QM team to present the solution.
So in the first part, there was a catalytic cycle given. You have to fill in the gaps and nothing else. You have to fill in the 4 gaps. So first, it was given this complex. The N4 is given in the sub figure on the left, top left, and OTF is the triplet CF3SO2. So from here you have been given that so a carboxylic acid and a half equivalent of hydrogen peroxide is added, and 2 equivalents, which are OTF2, is leaving. So half equivalent, because peroxide is an oxidizing agent, it can oxidize twice, H2O2. But here we need only one oxidizer, like Mn2 should be oxidized to Mn3 only. That's why we're using half equivalent. So the structure will be, I will draw here. So this is the first part. And now you can see, if you remember the electronic configuration, Mn2 is 3d5. 3d5 should be more stable because all 5 electrons will be aligned in the same direction, the spin. But we want to go from Mn2 to Mn3. Mn3 is 3d4. It is this stable. So why is it going? What's the reason? So the reason is, you can see here, intramolecular hydrogen bonding. That is making it more stable. So this is the first part, and if you figure it out, the rest is just E. You have to remove an H2O. So from here, an OH is removed and an H is removed. So you will get something like this. With an oxidation state of 5. After that, it was mentioned that in the chair configuration of the cyclohexane, a homolytic splitting is occurring. So what will happen? It will gain a radical H dot. It gained an H dot and its oxidation state changed from 5 to 4. After this, it is mentioned that the radical which was formed, the cyclohexyl radical which was formed, it is oxidized to OH. So it is getting an OH dot radical. So what it means, it splits and you get just with oxidation state of 2, and again if you add here H2O2, you will get this thing back. This was the catalytic cycle. After this, in part B, we have been given 4 carboxylic acids, and we have to figure out which one will give the best yield and which one will give the worst yield. So the best yield will be given by the one, as you can see here. Where is the R group here? R group is here. How will it easily form the hydrogen bond? If it's less steric, if it's more steric, then its alignment is not possible to be like this. And also, it should be less electrophilic. If it's more electrophilic, it can't be able to form this. Hence, the best one is the one which has the least steric hindrance. And the least steric hindrance is this one. This is the best. And this is the worst. In part C, we were given that the catalyst, we are changing the catalyst. And also one more thing to clarify, if you thought in the part C you have been given this, it doesn't necessarily mean that you will get the highest yield. Maybe you are getting the highest yield with this in a particular catalyst. But if you change the catalyst, maybe the reaction cannot occur. We are just giving you one condition. It is not that we are using this, it is stable. So don't think about it. After this, we have been given, we have to find out the increasing order or decreasing order, whatever you wish, of the enantiomeric excess, or which one is producing more enantiomer, one enantiomer than the other. So how to produce one enantiomer? You can only produce enantiomeric excess if you block one phase. How will you block the phase? It should be more steric. So the one which is more steric will produce an enantiomeric excess. So here you can see this first thing. It has 2 cyclopentyl group in a spirolectin and a TRIPS group, triisopropyl silyrene. It is highly steric. So it will produce high enantiomeric excess, correct? After that, you see that there is a cyclohexyl group, and again there are two cyclopentyl groups. So which one is steric? Cyclopentyl one. So because there are two rings. After this, you have the cyclohexyl. And why have we left the CF3? You can see the CF3, it is electron withdrawing. Again, the same reasoning which we gave here for the intramolecular hydrogen bonding. If you have electron withdrawing group here, again it will be disrupted. You can't form a stable intramolecular hydrogen bonding. It will, the catalyst will, the product will not be formed first at all. So if the product is formed, it will be randomized. It will not show any enantiomeric selectivity here because the product will be randomized. You have not a stable bond here. So it will not show much enantiomeric excess at all. Hence, the order is, I will write in decreasing order. This was the order. Any doubt? I presume there are no doubts. Right.
If there are no doubts, we will proceed with the next question. Team ISC, you do not have a choice since all the other questions have been taken. The question you will get is severe FOMO. Don't worry, no team is missing out. Guy, trademark, a budding math enthusiast from the physics department, has severe FOMO, fear of molecular orbitals. He decides to get over this fear and look into the chemistry side of life. He searches for the most physicsy, quantumy chemistry he can find and stumbles upon an interesting molecule. Hexacus phenyl selenyl benzene. The molecule looks cursed enough to him, so he decides to try and investigate it. He gets his close friend, Kem, to run an X-ray crystallographic study on the molecule after he treats it with two equivalents of NOSBF6 in cyanomethane, which is known to be an oxidizing agent, on a sneaky suggestion by Kem. Here are the results provided to Guy. These are the results. Kem said this figure was self-explanatory. Kem was lying. Here are the questions. Question 1. Figure out the charge on the molecule. Question 2. Figure out the possible structures of this charged species. Not the three-dimensional structure, the electronic picture, where and how the bonds are. Pay special attention to the orbitals. Question 3. Kem finds that the selenium atoms are equally spaced in the molecule. What structure that you figured out earlier is now ruled out? Question 4. To find a reason for why the selenium atoms are equally spaced, Kem runs a secret calculation and doesn't tell Guy what he did. Guy now has actual FOMO. He does decide to give Guy the data for this and some other molecules. Figure out what this calculation is Figure out what this calculation is measuring in these compounds. Note, this calculation relates only to electronic effects and not to structural effects. For example, the number of hydrogen atoms is not what the calculation is finding. The data is given. Question 5. Figure out how the above calculation helps you in explaining the distances between all the selenium atoms. Any doubts? Once again, are there any doubts? Since there are no doubts, your 15 minutes for thinking starts now.
When you say in A, figure the charge of the molecule, do you mean the full A structure or just the B structure?
No. The thing that's given in the B structure.
Okay.
Part 1 they have asked figure out the charge on the molecule. Which molecule are they asking? The one in A or the one in B?
B. The thing in the B.
The original
you have to
molecule.
figure out the
Okay.
charge on it.
Like in the third question, what does this statement mean? Like selenium atoms are equally spaced.
So if you compute the distance between two selenium atoms that are adjacent to each other, it comes out to be similar for all the selenium atoms.
So like, is it not there in the second part? Like, Or like in second part, we need to consider like all the like seeing the X-ray structure, we need to consider it.
Not even the X-ray structure. Second part, you just need to produce the bond line structures that you can form. All the bond line structures you can form.
Okay, so in the second part, selenium atoms cannot be equally spaced as well.
Could be, could not be.
Yeah, could be, could not be.
Five minutes remaining.
Like in the second and third question, like the selenium atoms are equally spaced, so is it considered like after reacting with NOSBF6 or the previous
After
case?
the reaction.
After the reaction.
1 minute remaining. Thirty seconds remaining. The 15 minutes for thinking are over. I see you now have 5 minutes to present your solution. Your time begins now.
So the first one, our claim is the charge of the molecule has to be plus 2. It's not very exact, but the claim is basically you can see the X-ray diffraction there is SbF6, 2 such molecules. Now for Sb, you know that the inner pair plus 3 is going to be more stable than plus 5. So there's a reduction of Sb from plus 5 to, okay, there is a reduction from plus 5 to plus 3, and since there are more molecules, total reduction in both the molecules is plus 4. From the exercise, it is also evident that if Sb is plus 3, the negative charge contribution of SbF3 is 6, since there are 2 such molecules. Now, so the molecule should be also neutral, otherwise it would be just flying here and there. So the structure in the X-ray must be plus 6, apart from the SbF3 3 minuses. And since plus 6 is derived from oxidation, where 4 electrons are already abstracted from it, so the original molecule must have a charge of plus 2, and hence plus 2 will be right. For the second part, my hypothesis is that for the second part, we think that there are certain possible structures. One is of course the one given by B. One is if you have a charge on say two different, some random SE. I'm saying that 1 plus 2 is there, so maybe 1 SE is somewhere here, and the rest of the SEs are close to it because of the plus charge. Possible. One of them will be 2 plus 1 charges on 2 different SEs. Oh, sorry for this. And similar thing, one of them would be, one of the structure would be B, one of the structure would be like this, and one of them would be 2 SE plus 1s, and they are going to have very high separation, followed by, and there is a ring somewhat like that. And something like that. So for the third part, we can see that we can say that SE are equally spaced, but definitely means the ones that are nearer. This structure and this structure is going to be avoided in part 3. So that is what is below, along with some other structures which we are unfortunately unable to figure out.
So for like part 3, the whole point is that even if the positive charge is not, the positive charge is delocalized. So due to the benzene being the positive charge is delocalized, so it will be spread equally over all SE. So there will be a partial bond over there. Yes. What?
For the fourth part, it might be something related to energy value, relative energy value related to some.
1 minute remaining. Thirty seconds remaining. I see your time is up. IT Madras, your 3 minutes for solving start now.
Yeah, so in first question, the NO SBF6, NO has +1 charge. So NO +1 will get reduced to NO gas, which will, and as it has, as we are given that there are two equivalents of NO SBF6. So as NO is reduced to NO, so 2 electrons will be required for it, which will be released by the molecule, and the charge will be +2 on the overall molecule. In the second question, as we are asked the possible structures, we think, yeah, as this structure is drawn here, like He will give its lone pair to the middle benzene ring, and here and here, as it will get a negative charge, so it will take 2 electrons out of it, and here we can, as there will be plus charge, so we can just create a double bond which will form the structure. And by resonance itself, we can also form this structure. So we will just have a like electron cloud like this. And we believe that for equally spaced selenium atoms, this structure will stay intact. Like we will consider this as the selenium atoms are equally spaced. And for other possible structures, we were also thinking of like we have to receive +2 charge in the molecule. So there are 2 options. Like either we do +1 charge, or we give +2 charge in the selenium atom, in one selenium atom itself. So what we can do is we can just by the same mechanism, we are just thinking of like having a +2 charge here and the same thing as here. And for the first
question 4, we can see this is purely due to electronic effects, because cyclohexene and benzene, if we compare, so cyclohexene has a 0.1 which is positive, and benzene has -13.2. Ions which have more electronic effect have a -25.4. So for the original molecule, I can say that if I have a more resonance, then my value will be less negative. So this structure which is possible has a less negative value than this second structure, and this also justifies our claim that this has an equally spaced selenium atom, since this structure will have a varying bond length here, and due to double bonds, this bond length will be less, and hence this angle will be less as compared to the others. So this is an equally spaced structure. For the fifth part, explain the fifth part just now. Yeah, so for yeah, in this like we are considering this molecule.
Your time is up. IISER Bhopal, you have 2 minutes to present your solution. Your time starts now.
For the first question, we have NO plus and SBF6 minus. So for the entire compound, since 2 SBF6 are joining, the molecule will have a +2 charge. Then for the second question, the selenium in the compound is having the orbital as sp3, and the carbon is sp2 hybridized. So this will have the HOMO, and this has empty p orbitals, selenium. So the sp2 carbon can donate some of its electron to the empty orbitals of the selenium. Hence, the bond can be formed. So now, according to this, since selenium is sp3, it should have a kind of tetrahedral geometry, and the carbon should have a planar geometry. But what is happening for the third part? But what is happening is, since there are a lot of other benzene rings around it, the molecule is actually not a tetrahedral, and it is in the same plane. So all of the selenium are in the same plane, and the adjoining benzenes are also coplanar. So hence this is the MO diagram for the SP, like the bond formation.
IISER Bhopal's time is up. IIT Delhi, your 2 minutes to present your solution starts now.
So for part 1, we recognize that a redox reaction is happening which causes charge to transfer. We have two possibilities for NO plus and sp5 plus. We notice that the reaction with NO plus is taking place because NO is escaping as a gas from the lattice. The charge species is not present in the final structure obtained after the X-ray. So the electrons are transferring from NO to NO plus to NO, which causes positive +2 charge on the molecule at the selenium atoms. Out of the distributions, we have multiple possibilities drawing on the board. So we have +2 to 1 selenium and 0 to all others. We have +1 at ortho, meta, and para positions respectively. Out of these, we will rule out +2 immediately because of symmetry concerns and also stability concerns. It is easier to ionize selenium than selenium plus. We will also rule out the meta distributions. Again, because after you draw the resonance structures, this is not going to give even charge distribution to all the positions. We notice that ortho and para are reasonably stable, where para will be the most stable. Supported by the fact in the X-ray structure, we have rings in pairs of 3 pointing up and down, which causes us to believe para is the structure we're looking for.
We conclude that in the fourth question, the calculation that was missing was the resonance energy. As we can see in the original molecule, the resonance energy was less negative than the ion. In the ions, the selenium gets positively charged. Hence, there can be more effective resonance between all the rings. Also, in the fifth question, we can tell that higher the resonance energy, higher will be the bond orders, and hence shorter will be the bonds. Hence, in the ions, the distance between the selenium atoms would be smaller as compared to the original atom, as the sp2
Your time is up. Please stop writing. Please stop writing on the board. Judges, do you have any questions or clarifications?
Yes, I will have one from IISc team. What do you mean by partial selenium bond? You have used this word.
I just mean that there will be resonance that will be happening in this structure. So in certain resonating structures, there will be pi bond because the benzene ring
pi bond between
selenium and carbon, and in other
fine, thank you. IISER Bhopal, what do you mean by coplanar?
All of the benzene rings are in the same plane. So they do not have, the 3 of the benzene rings are in the same plane. So they do not have a lot of steric hindrance in that case.
Do the judges have any more questions? Since the judges are done with their questions, I request a member of the question making team to present the solution.
So For the first question, it was pretty simple to figure out that the charge on the molecule is +2 because there's two SBF6 minus units hanging around one molecule. So it has to have a +2 charge. Now for the second question, what you had to figure out was you have this. You have 6 seleniums, right? The only place that the NOSBF6 is going to get an electron from is the seleniums. Only they can get oxidized, right? Now there are multiple possibilities. First, you could just get a +2 charge here, right? That's one possibility. One you could do is you have a +1 and this will be a radical because a selenium has a lone pair which will lose one of its electrons. You get one lone pair here, one lone pair here, right? That's a structure that will eventually, if you draw the resonance, lead to this. Cool. This is one of the structures. Now, for question 3, you see this distance has to be smaller than this distance. It has to be, right? So this and this can never be equal. This is smaller than this. So these distances have to be different. So we have to rule out this structure. Now, why it's written pay special attention to the orbitals is because this happens. I'll just draw it here, I guess. Seleniums have p orbitals, right? If you look closely, they can do this. If you remember 3C2E bonding from like class 11th, I guess, does something very similar. So the positive 2 charge is actually delocalized over the entire selenium thing. Now, this will form like a ring structure, which is a partial bond-like character between all the seleniums, which is why they end up being equally spaced in the final structure. For question 4, if you look closely at the data, the major difference between cyclohexane and benzene, the major electronic difference that is that benzene is aromatic, cyclohexane is not. So the calculation straightforward gives you a quantitative idea of the degree of aromaticity in the molecule. So now if you look on the data for the molecule, the original molecule has a data value of -7.8, right? And benzene has a higher negative value than cyclohexane and a higher aromaticity. So a higher negative value for the ion means the ion is more aromatic than the original molecule. More aromatic means you have the original benzene ring in the middle, and somehow this entire electronic structure that is being formed also turns out to be aromatic. This is a form of sigma aromaticity, which is quite different from what we learn as pi aromaticity. One more very hand-wavy explanation to this would be, you have 6 seleniums, 2 lone pairs per selenium, remove 2 electrons, that's 10 electrons in this ring. That's 4n plus 2. That's also aromatic. Yeah, so the question 5 is just straightforward. This calculation is telling you that this thing is aromatic. So this will put major contribution into the resonance hybrid of whatever this molecule is going to form, which makes the selenium atoms equally spaced. Any questions? Yeah.
Like when you draw that like +1 charge on Se and +1 charge on the para position of Se, so won't it do like other Se atoms, won't it do resonance with that plus charge? So that plus charge gets equally distributed, like +1/3, +1/3, +1, like all Ses will get +1/3 type charge.
Yeah, they will, and then their p orbitals will start interacting.
Yeah, so like what that the argument that you have given that they have different bond lengths, so they won't be equally spaced. So because of that resonance, as the electron cloud is getting distributed, so it's more sort of a
what you're talking about is the resonance hybrid.
Yeah.
What the question asked you for was possible bond length structures. They're not resonance hybrids.
No, in the second question it was asked like the possible products that that are possible. So if suppose this SE plus and SE plus, they are existing in para form, so it must be existing in the resonate, like yeah, the resonance must be happening. So it's a more kind of a symmetric molecule rather than like plus charge accumulated on the para positions with double bond, like staying at the para positions only. So won't it also give a equally spaced SE setup?
See,
That was our like we were thinking in that direction. So like if you can clarify.
yeah, if you
Marcel, it's what you are telling. As you at the end part, you listen. 4n plus 2. Huh?
Actually,
The
that was
electrons-
that was fourth and fifth question. So we didn't.
No,
think
then
of-
the first part of the
Yeah.
question you're asking, this is very well established sigma aromaticity. Sigma aromaticity. So there is whatever drawing you are trying to understand in terms of resonance. That end product is the sigma aromaticity. That will be just the beginning part. Double bond, single bond, but that is your understanding culminating into the sigma aromaticity.
what you're saying is true. That's also a part of the resonance hybrid. And when you do make that structure, in real life, this is also a driving factor to the same structure that you are talking about. What you're saying is correct. The plus charge is delocalized over all of these. You could make resonance hybrids with here, charge here and here, charge here and here. It's fine. At the end, when you make the most probable structure, which is this, which is again exactly what you are also talking about, the positive charge is indeed delocalized over all seleniums. You drew the correct structure.
Yeah, like actually we didn't see the best possible. Like we just see like if it is equally spaced and as the resonance hybrid is like distributing the charge like in all SE atoms, so it would be having a equally spaced like SE setup.
Yeah. That statement is true.
Okay.
Any more questions?
Since there are no more questions, this brings us to the conclusion of Chemistry Deep Thought of Mimamsa 2026. We thank you all for attending and hope you enjoyed. We once again thank our judges for attending this event. We currently have SciCon, the Science Convention, and ISEC, the Interschool Science Exhibition Competition going on at the lecture complex. We will be back with rapid fire this afternoon. 3 o'clock.
Also, lunch will be served at dining hall complex first floor. Please proceed there. Okay, no, wait. Some of you will have to go for participant interviews. The others will go to lunch. Please follow your... No? Okay, please proceed to lunch. We'll have the participant interviews later. Follow your team coordinators.